well, we start our seminar. And let's try to rewrite some system of differential equations in the polar form. So rewrite the system in the polar form. Y prime, so x prime minus a is a constant times y, and y prime equals ax. Follow, do you want to go to the blackboard? Welcome. It is a green board, not blackboard. It is a green board. Right. Then x prime. We must differentiate the product, apply the product rule to differentiation of the product r cos theta. Correct. Then we should first eliminate theta prime and eliminate r prime. So what shall we do to eliminate theta prime?
Cos and
multiplied by cos theta, and multiplied, the second one should be multiplied by sine theta. So we need not write x prime, right? X prime, we need not x prime. So
yeah, I'm just writing what's on the left
right. So
okay,
on the starting from this.
Okay. Is it minus a r sine theta?
Yes.
Theta, right? Minus r, minus a times r times sine theta.
Oh, this will also be cos of 0.
So why are we eliminating r prime first? Can we also eliminate theta prime first?
Yeah, of course, yes. So it doesn't matter. The order doesn't matter. We can eliminate r prime first or theta prime first, and then r prime first. So I prime, it doesn't matter.
I don't understand. Get the equal to minus a r sine theta.
So to get, how to get which? So this,
yeah,
just substitute. So x prime is equal to minus a times y. So we must substitute r sine theta for y and obtain this.
So he says x tag equals to r prime cos theta minus.
Okay, so we apply product rule to differentiate this product. And next, x prime must be equal to minus a y. So we substitute r sine theta for y and obtain the right hand side. So if we multiply by Sine and so I think you must change the sign. So minus sine theta, minus to get 1, to get the basic trigonometric identity. You must multiply not by sine theta, but by minus sine. I will write. Put minus there. Right. Plus then. Right. Right. So this is correct.
Can divide by r. I'll just erase it. We can divide by r.
Okay. Right. Equals A. And so the answer is so write these two equations as a system of differential equations. R prime equals 0 and theta prime equals A. These two equations can be solved. R is a constant and theta is equal to A multiplied by T. Let's see, right? R is a constant. Plus C2, I think. Plus C2. Right, correct. And if we want to, thank you, follow. And how to obtain the second? How to calculate this? First, so multiply the first equation by minus sine theta, the second one by cos theta, add them together, and we will get this and multiplied by r, and r here. And after this, he eliminated r, cancelled it out from the both sides, divide both sides by r, and so he has divided in this manner.
So when he does r tag equal to 0, then he integrates r to get r equals to C1. So
Well, because it can be easily integrated. If r prime is 0, then r is constant. And
constant to
C2, right? C2, because theta prime equals A is integrated, so we can integrate both parts, and so theta is equal to AT plus C2, so it is integrated. And so if we want to look at the phase trajectories, so at the projections of integral curves on xy plane, in xy plane. So I don't want to draw t, but only in xy plane, we can see that r is constant, r remains constant, and theta is equal to AT plus C2. This means that the trajectories will look like the circles centered at the origin. These are trajectories. If we start from this point, we will move this way. Or if we add the third dimension, the t-axis, then we will see the spiral not damped, so damped spiral, right? Damped spiral, as before it was damped spiral when it becomes closer and closer to the t-axis, but here it is not damped, it is regular spiral. Yes. Yes. And so in what follows, we will study how to solve these linear equations, the systems of linear equations for arbitrary A, B. So it will look like so AX plus BY, Y prime equals CX plus DY. and we will study how to solve, so the algorithm for solving this linear system. It will not be necessary the spiral, it will behave in different ways, and so you will be familiar with this different behavior, and you will be able to determine, to specify the behavior from the matrix A, B, C, D. Using the properties of this matrix, you will be able to determine the behavior of the solution of this linear system. So this is our closest goal of our study, and so we will discuss this next time. But today we will discuss several theoretical questions, so we should finish theoretical discussion. Task number 2. Okay, so we can see that the second order equation and let's try to answer the following question. For which initial values does the second order equation have a unique solution? For which initial values does this second order equation have a unique solution? The initial values for the unique solution. So let's start with the initial values. So in this lecture, today's lecture, and preceding lecture, we have discussed second order vector equations. But here we have one, so first order equations. We have discussed first order vector equations, but here we have the second order differential equation. What about the initial conditions, and what about the application of the Picard-Lindelöf theorem? Can it be applied to this second order equation? Can you answer this question?
Yes.
How to apply? Don't know. Who knows how to apply Picard-Lindelöf theorem to one second order equation?
Well, perhaps you express second order as 2 first order?
Right. So to introduce the additional, right, extra variable. So in this manner, for example, x1 will be equal to x, x2 is x prime. Then we will have, so this second order equation is equivalent to the following: x1 prime is equal to x2. So x prime is equal to x prime. So right? So if we differentiate x, we will get x prime. So this is true for the beginning of these two equations, right? x1 prime equals x2. Clear? Next, x2 prime. What is x2 prime? It is x2 primes. And so we can rewrite it as tan x1 plus cube root of t. So this second order equation is equivalent to 2 first order equations, right? And we can apply the Picard-Lindelöf theorem to this system, linear system. The solution exists locally. The solution exists and unique, and is unique for. So if we take any t0. So x1 0, I will put it here, and x2 0. So given any initial condition, the solution locally, solution exists and unique. But what about the requirements, restriction, conditions on x1 0 and x2 0? Can they be arbitrary or not? To answer this question, we should look at f, the function f. This is a vector function f. To apply Picard-Lindelöf theorem, right, we must check the assumptions, the hypothesis of this theorem. The function must be continuous in all the variables, and it must be locally Lipschitz in the variables x1 and x2. Okay, the function has a continuous partial derivative with respect to x2. So we know that if our function is C1, then it is locally Lipschitz. Let it be Lipschitz. So a partial derivative with respect to x2 exists and continuous, so it's okay with x2. x20 can be arbitrary. But what about x10? Look at tan x1. The function tan x1 is not defined for several values of x1, and so it is even not defined, and so it is not locally Lipschitz, and this in the neighborhood of these points at which tan x is not defined. Okay, so tan x1 is not defined. If x1 equals pi half plus pi k, where k is an integer number, right? So x10 can't be of this form, right? So the answer to this problem is, so t0 and x20 are arbitrary. And x10 is not equal to pi half plus pi k. Chi is an integer number. And let's turn back to our original equation. Arbitrary. C1. Is C1. What is C1? So f is C1 so with respect to x2. So this means that partial derivatives of both components of f with respect to x2 exist and continuous. If we consider the partial derivative of this with respect to x2, we'll get 1. So it exists and it is continuous. So this means that okay, and if we differentiate the second component with respect to x2, we'll get 0. So both functions exist and continuous. So this means that our function is C1 is of class C1 with respect to x2. So x2 can be, so it is Lipschitz, and x2 is arbitrary. But what about x1? This function, the second component of this function, is not defined for at this point for if x1 has this form. And so this means that we must exclude these points from our initial conditions. Okay, right. And if we go back to this second order equation, we can say that t0 is an arbitrary. x1 goes to x0, right? Because x1 is x. So x0 is arbitrary. And we need to specify x0 prime, which correspond to x2. And x0 prime should not be equal to pi half plus pi k. So this is the answer. I will write it in another way. So t0 x0 prime, where t0 x0 are arbitrary. And x0 prime should not be equal to this.
Okay, can you just start again that definition of arbitrary?
Arbitrary, any means any.
So
Arbitrary is any.
Any, okay, I understood, thank you.
Or arbitrary, any. Well, should we go further? Right? Let's go further. Okay, task number, I will write it down. Task number, so 1, 2, 3. Task number 3. How many solutions to the equation x, the nth derivative equals t plus x squared? How many solutions to this equation are there that satisfy initial conditions? So we are given an initial condition, x of 0 equals 1 and x prime of 0 equals 2. This, so this is an initial condition, or two initial conditions. Okay, how many solutions are there that satisfy these initial conditions? And we should consider, several values, different values of n. Consider cases n equals 1, n equals 2, and n equals 3, or n greater than 3. Oh, okay, so the question is to consider 3 cases, sorry. Let's consider these 3 cases. Okay, let's start with this. How many solutions are there satisfying these initial conditions? What about Picard-Lindelöf theorem? It guarantees the uniqueness and existence and uniqueness of a solution. In which case? If the right-hand side is continuous and locally Lipschitz in X. This is true, right? It is this function continuous? Yes, the function is continuous. Is it locally Lipschitz in X? So we can find the derivative with respect to X. Right, so locally Lipschitz in X, continuous locally Lipschitz in X. Then look at this initial condition. We have one extra, so additional condition, I don't like it. So the initial condition should be x of 0 equals 1. It's enough, right? Only one initial condition, not the second one.
And why don't you want to consider
because so the first order, because we have the first order equation, and so for the first order equation we need so the initial condition should be only the time and so the point, not the derivative. If we have the second order, let's look at the preceding task, the second order equation. Since the second order equation is equivalent to the system of first order equations, for the first order equation we need to know t0 and the values of these two functions at t0. And this initial condition goes to t0, x0, x0 prime. So for the second order, we need to know t0, x0, and x0 prime. For the third order equation, we need to know t0, x0, x0 prime, and x0 double prime, right? So it works in this way. So for our equation, this is an extra condition. But maybe it can be satisfied. So Is there at least one? So, okay, Picard-Lindelof theorem guarantees that given this initial condition, we have a unique solution of this equation locally in the neighborhood of 0, in some neighborhood of 0. We have a unique solution. But what about the second condition? Is it possible to find a solution that satisfies both initial conditions? It is not from, so the second condition is not from the initial value problem. It is not from the Picard-Lindelof theorem, but maybe it is possible to satisfy both conditions. Is it possible for the trajectory to satisfy both conditions or not? How can we check it? Why? Right, the answer is to substitute. So to answer this question, we should consider the original equation and satisfy 0 for t, 1 for x, and find x prime, right? So if t equals 0, x equals 1, so they are taken from this initial condition. Let's find x prime of 0. Our solution x must satisfy this differential equation. So x prime is given by this formula. So substitute 0 for t, substitute 1 for x. Is it clear? Right? And so we can find that x prime of 0 is equal to 1, not 2. Right? Not possible. But it is possible if it were 1, then it would be possible, right? For 2, it is not possible. So not possible. Sorry?
Suppose x tag 0 equals to 1.
Right.
So
it is possible. Right. Suppose this.
Okay, yeah.
Then the answer is the following. We are trying to solve this initial value problem. The answer exists and is unique. But at the point 0, we can compute x prime of 0 in this way.
Basically, we substitute for x 0.
Right. We substitute. So to find x prime at 0, we should substitute 0 for t and 1 for x and find x prime of 0.
And that will be the solution for the question, basically.
Right. And so since it is possible, then so the fact is, if the solution satisfies this initial condition, then it is necessarily satisfy this condition by this condition, by this equation, differential equation. It follows from the differential equation, right? But it is not possible for 2. Okay, case number 2. So this was for n equals 1. Case number 2, n equals 2. So let's consider this. So then, this is the set of initial conditions, right? 2. How many trajectories are there? How many solutions that satisfy this differential equation and this initial condition? Okay. Can you answer this question? How many solutions satisfy this differential equation and this initial value, these initial conditions? 1, right, by Picard-Lindelof theorem. It is exactly one solution because the function is very good, it is continuous and locally Lipschitz. So all the conditions, all the hypotheses of Picard-Lindelof theorem are satisfied, and so there is exactly one solution that satisfies this equation and satisfies these initial conditions. Exactly one. Can you so to find it, you must solve this solve this equation, but sometimes it is difficult. Maybe, so I don't know how to solve it.
Question: how do I know how many? It's like for this one, it's exactly one.
Right.
But how can I determine it? I don't understand.
Determine. So to find the question was how to find how to find this solution, satisfying this. So the answer is sometimes it is very difficult to solve a differential equation. We know some methods for solving differential equations, but sometimes it is difficult. There are no general algorithm for solving any differential equation.
Suppose I look at the question in front of me. So x tag tag equals to 2 plus x
Okay,
squared.
so to answer this question, so the idea is to answer this question, how many solutions are there? You need not be able to solve this differential equation. You may use theorems. So this is the role of theorems in our life. So to answer some questions, you need not find their solution. You may apply the theorem.
So for the second question, what theorem do I have to apply again?
So exactly one, because this equation satisfies Picard-Lindelof theorem. So then exactly one, but we need not be able to find the solution. Right. Next, so question number 3. If n equals 3, so what about x triple prime equals t plus x squared, and this initial condition, x of 0 equals 1, x prime of 0 equals 2. How many solutions to this equation satisfying these initial conditions? Do you know? Right, infinite. So what? How to prove this?
We have to use a Pin-Claviero theorem.
Right. We can use this Picard-Lindelof theorem, but we need to know x2 primes, right? Double prime of 0. We may set it to be equal to any value alpha, any value of the parameter alpha. So if we fix alpha, we get just exactly one solution to this differential equation, right? But alpha may be varied. We may vary alpha, so it may take different values. And then for each alpha, we will obtain different solutions, right? 2 solutions with 1 and 2 and different values of alpha will be different. So there will be, for example, 2 solutions with these 2 conditions. X of 0 is 1, x prime of 0 is 2, but x2 primes will at the point 0 will be different. So the functions are different, right? Well, and so since alpha may take infinitely many values, different values, and so we will have infinitely many different solutions for n equals 3. So this is the correct answer. Well, okay, how many? Okay, how many time? How much time do we have? Just a moment. 44. So maybe a break will be in 5 minutes, right? Or now in 5 minutes. Right. We will use this 5 minutes. Next, let's discuss the next question. The next task. Right. Right. So the question was, what happens if n is greater than 3? So I'd like to repeat the question. The question was, if n is greater than 3, then how many solutions do we have? And the answer is infinite, right? If we have x4, the fourth derivative, then there will be.
If n equals to 4 and we have 4 initial value problems.
Right, for the fourth order equation, we need 4 initial values from the function. So the derivative of order 0 is the function itself, up to the and the derivative of order n minus 1, right?
And in that case, it won't be infinite. The number of
So
it will be 1. Can we have a break now?
no, right. Let's have a break for. Right. Let's try to find. Let's discuss. I think let's discuss this task. It's task number 4. Right. For which values of n can the equation, the nth derivative of f of tx, where f and f prime with respect to x, so with respect to t, are continuous. In R2, have the following two functions as solutions. So find n, for which this equation has two solutions, the following two solutions. x1 equals t, and x2 equals t plus t squared. There are two solutions. Okay. Since we have this, we should, so are continuous. Then we can use, we can apply Picard-Lindelof theorem. Picard-Lindelof theorem. Okay, and let's try to consider different initial conditions. Let's take t equals 0, and we have x1 of 0 equals 0, and x2 of 0 equals 0. But these two solutions are different, right? So we have two solutions, and they are the same. They have only one point in common. This one. So the first solution is this, and the second solution is this is a parabola, right? So minus. So it looks like this. So what about the first order equation? Is it possible for this equation to have these two solutions? This equation having these two solutions. Does it contradict Picard-Lindelof theorem? For both solutions, we have this, but the functions are different.
Maybe you can include both of them.
Right, so it is impossible for these two functions to be the solutions for this equation.
Why?
So because the initial value problem has a unique solution, but there are two solutions. So you can see that we know nothing about the function. We don't know the function, but we know the statement of the Picard-Lindelof theorem, right? Picard-Lindelof theorem. If f is sufficiently is good enough, so these are continuous, then this initial value problem has a unique solution for this initial value, right? Well, so
Isn't the condition supposed to be f is continuous and locally it shifts.
So if this is continuous, then it is mathematical locally Lipschitz, right? Locally Lipschitz. Well, to find n. So n cannot be equal to 1, right? N is not 1. So this is the first part. Then n is not 1. Okay, let's try n equals 2. Maybe 2 is good. So let's consider the initial value problem. X of 0 equals 0. And what about x prime of 0? So you should differentiate these two functions and find their derivative at t equals 0. Differentiate this with respect to t. The derivative is 1. Here the derivative is 1 plus 2t, but if we substitute 0 for t, we will get 1 again. Again, 1, so this is the initial value problem, and again, there exists a unique solution satisfying this. So n is not 2, because we want these two solutions to be, these two functions to be solutions. But this initial value problem has a unique solution, and not two different solutions. Difficult. Is it difficult to find the order and the order of this differential equation such that these two functions are two solutions? For n equals 1, it is not possible. These two functions so can't satisfy this initial. Picard-Lindelof theorem, yeah. Right? So if the function is good enough, so it is continuous and locally Lipschitz, then locally there exists a solution, and it is unique in the neighborhood of the point t0. So if we apply Picard-Lindelof theorem to our situation, it says that locally in the neighborhood of 0, the solution of this initial value problem exists and is unique. But these two functions, so we don't know f, but we can see that these two functions satisfy this initial condition. But this contradicts the uniqueness of the solution. Uniqueness, because these are two different solutions. Well,
can you please repeat the name of the theorem you just said? It's called the
Picard-Lindelof theorem. Picard is the French mathematician. Picard-Lindelof. Picard. So D is not pronounced, I think, right? Picard-Lindelof. Then 3. Step number 3. Let's consider this x triple prime f of tx. X of 0 equals 0. X prime of 0 equals 1. What about x2 primes of 0? Zero and 2, right? So if we find the second derivative of this function, we will get 0. So if we write 0, then there is a unique function satisfying these conditions, and it may be this function. If we consider the second, so different initial value problem, x triple prime equals f of tx, and different initial conditions. What is x double prime? Let's find the second derivative of this function. 2. Okay, so the second function satisfies this initial condition, so it doesn't contradict Picard-Lindelof theorem. So it is possible to find a function f such that so these two different initial value problems have a unique solution each. But now, so the last step is to find their function. Is it possible to find this function or not?
I think it is possible.
X triple prime equals what? So the answer is very, very easy. It must be X triple prime equals 0. Okay, let's try to solve this. Just a moment. I will try to answer. X double prime of 0 equals 1. Let's try to solve this initial value problem. Do you understand why we need to find f? Maybe suppose there is no such f that these conditions are satisfied and this is the solution, or this is the solution. Maybe it is not possible to find f, such f. But I claim that it is possible. Let's try to solve this. X triple prime equals 0. This means that x double prime equals constant, C1. Just integrate once, then integrate twice, and we will get C1t plus C2. And so, x double prime, so x equals C1t squared half plus C2t plus C3.
Why do we integrate C1? We get C1t plus C2. What's the reason for that?
So how to solve x prime equals the function f of t? How to solve this differential equation? The variables are separated. Or maybe, the first way is to separate variables. And then integrate. I thought to do this in the differential equations, but you have discussed this equation in calculus. So given a derivative, how to find the primitive, or to find the antiderivative or primitive, they are the same. Just to integrate. This is the beginning of the calculus of integration, right? Okay, so I think it's clear. And now, given these three requirements, we can find C1, C2, and C3.
I mean, the reason I asked that is because C1, I thought it was the X. Okay, I made a mistake. Yeah. I know what you're talking about.
Right. So how to find C1, C2, and C3? So it can be done using this. So x double prime of 0 should be equal to 0. So we can see that C1 is 0. From this condition, C1 is 0. Then x prime of 0 should be equal to 1. So C2 is 1. And C3 is 0, right? C3 is 0, right? And so the answer is, right, x equals t is the solution to this initial value problem.
Okay, can I ask a question? So for the 3, why do we have 2 separate parts again?
Because so let's look at them task. So our task was the following. What was the task? So we have this differential equation of order n. F is sufficiently good. Is good enough, I think. F is good enough. We have 2 solutions. The task was for which value of n it is possible. Is it possible to have 2 different solutions? the answer is so n should be 3. So it is not possible for n equals 1. It is not possible for n equals 2, and it is possible for n equals 3 and for any larger n, right? So this proves that it is not possible for n equals 1. This is proof that 2, right? So I have found these initial conditions from this solution. So if we have this solution, and if we substitute 0 for t, we can see that x of 0 is 0. Try to substitute 0 for t. Then x prime of 0 is 1, and x double prime of 0 is 0.
So what if we do the same for
Right, and do the same for this. So we go back from the solutions to the initial conditions. Having two solutions, we can find two initial conditions.
But why can we find two initial conditions for n equals to 2? Because it doesn't satisfy.
So just differentiate and substitute 0, right? And then we have, so the solution to this initial value problem is x equals 2. And similarly, if we solve this, if we solve x triple prime equals 0, x of 0 equals 0, x prime of 0 equals 1, and x2 primes of double prime of 0 equals 2, then we will get x2 equals t plus t squared.
Is initial value, we're trying to get the initial value equation.
Initial value problem. Initial value problem.
What does that mean?
Initial value problem means that we have a differential equation and initial conditions. So we must have a differential equation plus initial conditions. This is called initial value problem.
So it's a differential equation which satisfies
With initial conditions, right? This is the answer. Okay, it was task number 4. Now let's discuss the maximal interval. Maximal interval.
this one we can do.
Right. So the maximal interval for 5, task number 5. Let's consider the initial value problem of this form: minus x squared, x of 1 equals negative 1. Let's find, it can be solved. So this equation can be solved. We can find the solution and find the maximal interval. Okay, who want to solve? Not follow, but maybe somebody else. Ashish, can you solve this? Ashish? And Rohan? No, Santiago. Misha, no, Kafi, yeah, I think. Misha, do you want to solve? Next Kafi, right? Kafi will be next.
Another question?
Hmm?
Another question? Should you have a
I don't know, so follow the time, follow time.
The interval.
Uh-huh.
The maximal interval. Right?
Maximal, so find the solution at the maximal interval. Solution and maximal interval.
Well, the equation is separable.
And it can be solved.
And it can be solved, right? So rewrite it first.
So it's better to separate variables.
Oh, right.
So write x prime as dx over dt. Correct. Then integrate.
So
Usually t plus c, so add constant to t.
on this side.
Right, but it's better to add the constant here to t, t plus c. Usually the constant is added to the independent variable, to time. Right. Just the table.
Yeah, it's just the power, just the regular
Power, right, plus 1 to the power.
So the minuses will cancel. And we just get 1 over x.
1 over x, correct. No plus c, so it's okay. Then x is equal to
1 over t plus c.
T plus c, correct.
So
Okay, you have lost a zero solution, identical zero, but we need not know it because we have these initial conditions. A zero solution doesn't satisfy this condition, so it's okay. Right, from this initial condition, right? You're right. Use that space,
here,
this part of the blackboard.
So we put in 1 for t and minus 1
for right. I will repeat for the listeners. So you put 1 for t and minus 1 for x to find c, to find the constant. Correct. Then solve this equation.
Well, we just flip it. So 1 plus c equals e equals
minus 1, right?
1. So c equals 1.
C equals minus 2, correct. Then substitute. Plug down. Yeah. Plug there. T minus. Right. This is a solution, and then the maximal interval.
So it's similar to what we did in class. So it's hyperbolic. With an
right.
asymptote
Hyperbolic, correct.
At 2.
Right. So it stops at 2. Right. 2 is an asymptote. T equals 2 is an asymptote, but the problem is to take the left-hand part of the or the right-hand part, right? So the straight line, vertical straight line, t equals 2. Separate our plane into two subspaces, right? Two sub.
The horizontal asymptote.
So. T must be less than 2. It comes from this initial condition. So there are two branches of the hyperbola, right? And so we must consider this part because we have an initial condition. Initial condition, so it is 2. The initial condition was this. So -1, -1. So you should draw. So I think not. So we should correct. We should fix the. I will take. Right. The correct is this, I think, because it is plus t. If we compare with that, no. So it must be this hyperbola, right? And so we have for t equals 1, we have this initial condition, right? And so we must take this branch of hyperbola. So t belongs to the interval from -infinity to 2. So this is the answer. This is the solution, and this is the maximal interval. Okay, look at this. Maybe, sit down, please. Thank you. And to complete this seminar, so I want to discuss one more task, I will do it myself, and so it will not take much time, right? So to finish this, because so I don't want to come back to this problem next time, so I want to finish. The problem is to prove that the maximal integral is R, is the entire real line for the following. So it's task number 6 for the following initial value problem: x plus 2t squared sine squared x, x of 0 equals 0. We consider this initial value problem and want to show the maximal interval is the entire real line R. How to prove this? Okay, we can use the last theorem. So okay, solution is very easy. We will use theorem number 3. By theorem number 3, we must show that the absolute value of this function of this right-hand side doesn't exceed a, depending of t, times the norm of x. So now I write the modulus, the absolute value of f, because it is one-dimensional case, and so the norm is just the absolute value, right? Plus b of t. Let's try to find this and this. If it is possible, then this will prove, by theorem number 3, this will prove that the maximal interval is R. Okay, let's try to estimate f. It is x plus 2t squared sine squared x.
A and B are the endpoints of the interval, right? The maximum interval.
Right, interval. So, but if we take R for the interval, so theorem 3 can be applied to R. I can be taken to be the entire real line. And so if this inequality is true for the entire, for any t from R, then the solution is defined in R.
In other words, that A and B equals to minus infinity and 1.
But so they should be finite and continuous, right? So by triangle inequality, it is less than or equal to the absolute value of x plus 2t squared sine squared x. If we compare these two inequalities, then we can see that A is the coefficient of the absolute value of x. So A of t can be taken to be 1. What about B? So B must depend only on t, not on x. But sine squared x doesn't exceed 1, right? It's less than or equal to 1. So it is less than or equal to x plus 2t squared. So A is 1, B is 2t squared. So this condition is satisfied. So by theorem number 3, the solution exists on the entire real line, right? So that's all. I think it's fine to finish. Thank you for your attention.
I wanted to give the teacher the privilege to prove it. Thank you very much.
Thank you. See you later. I'm very glad to see you, all of you, right? So you are here in Moscow.